back to the class. See, I told you that for second order, that is for beta value, beta values, what do we need? We need donor one side, acceptor one side, in the middle pi, like this is a pi system, aromatic pi system, okay. And so this is, so therefore it is donor pi and acceptor. As we increase the pi, so will the value of beta. For example, this para-nitroaniline in acetone gives 8 into 10 to the power minus 30 ESU unit. That is a unit into 10 to the power minus 30 unit. Okay. So, it is gives a value of 8, and in the same unit it gives the value of 55 when I comes to this one, it is called DANS, DANS, because here we have more. Here you have one benzene, two benzene, and then double bond. That means pi system is elongated, and thus when we increase the pi system, one thing happens. Okay. Once you increase the pi system in a molecule, then what will happen? Its beta value increases, but there is one caution, something called trade-off. What happens? Suppose when I excite this with light, okay, I am counting beta values. As I go down, the absorption maximum will come, absorption maximum of this stuff, this molecule will come to the longer and longer wavelengths. So, let me put it this way, this particular compound, suppose it gives here absorption maximum, this one will give little bit here. How about this? This may give all the way here, this is a visible range suppose, and these are UV range somewhere. So, if that happens, what is the problem? Problem is that this is emission, right? This beta value we get from emission, how much emit, how much is the non-linear optically, because of non-linear activity, how much is the beta value? It will always give less. Why? Because in this absorption some light will be absorbed. Suppose there was no peak, then what will happen? Suppose there is no peak, so my beta value will be so big, just suppose. Now, because this molecule itself absorbed, every molecule absorbs. So, where a molecule absorbs, we have to excite that place. So, it will emit and it will absorb also. So, because of this peak, my beta value will be erroneous. My beta value will be erroneous for this absorption peak. Erroneous means it will show lower value. That is why we have to use. So, therefore, after we know that this is the peak, this is my peak, then which light I am going to use? I am going to use a light here, because I have to light it up. You have to light it up, the material, and then it will give you beta value, gamma value, etc., etc. So, I have to heat it, heat this molecule, say DANS, with which light? Suppose DANS, suppose this one, this particular one, when n equal to 3 gives a peak here. So, this peak say around 400 nanometer. Therefore, which light I am going to use? I am going to use a light 1907, way down here, 1907. nanometer. So, this is called absorption transparency trade-off. This is called absorption transparency trade-off, okay? Because I have to use this light, and using this light I am going to see beta values, calculate beta values by looking at. So, therefore, you also understand why we always make, when we find out the beta values or gamma values, we always take zinc 2 plus, or say cadmium 2 plus, or say copper 1 plus, okay, because these are all D10 system. Being D10 system, they are all saturated, they are colorless. They are colorless means no absorption, okay, colorless, and not only they are colorless, they will not going to interfere with beta values. So, this is a very important, they have no spectroscopic signature, D10 being D10. So, these are the some of the salient features we have to remember. So, this is for beta and this is for gamma, because symmetric. See, both sides electron accepting and pi. So, A pi A, and this is D pi D. So, these are all symmetric. So, therefore, for beta values we want D pi A or asymmetric electron asymmetric, okay, electron polarization if you will, and for gamma value we always want symmetric electron delocalization. If we have symmetric electronic delocalization, gamma value will be high, and similarly beta value will be high when we have asymmetric delocalization. Okay, so, this is enough for this. You can read this and you might venture into going there, because this is a very, very important area of supramolecular chemistry. It has enormous possibilities in modern day photonics, because from defense to state of the art equipment and what not, this is a very, very important area, okay, optical nonlinearity. And as a chemist we can design different kinds of stuff. Okay. So, this is enough. I will, as I told already, I will give you I will give you one or two some typical references from where you can know further. My idea of teaching this course always has been, I introduce you to the main features of the current supramolecular chemistry, and any of you might be interested in a particular area, then with the references you can go ahead. Okay. Now, I will tell you my last part of this with light. Okay. So, I will tell you a phenomenon. Okay. The phenomenon is as such. Let me first draw a protein. I cannot draw a protein, but I am trying. Okay. I am trying to draw a protein. I can show you what a protein looks like. This is the one, a protein, how protein looks like. Okay. So, first let us see the problem, then we take solution slowly. So, this is my protein. Okay. So, this is my protein, this funny looking structure is protein. Okay. This is beyond me to calculate. Okay. This protein means you have amino acids, polyamino acids, okay, protein, Out of that 20 essential amino acids that we have, 3 phenylalanine, tyrosine, and tryptophan. These 3 amino acids are fluorophores. They can act as fluorophore, because if you hit them with light, they can emit. Okay. So, they are fluorescence active, let us call it fluorescence active amino acids. There are 3. So, here I am telling you a story. In this protein, okay, let us make it little bit bigger. This is my protein. Okay. You do not see, I also cannot see what is the starting. See, one point I can see and other point I forgot. Oh, here. So, these are the 2. This is starting from here. So, amino and then acid part, carboxylate part. Okay. This is my protein. And in this protein, this is called active, this point, this is called, in this protein, this is called active site. Active site. Okay. There may be more than one active sites also, but mostly there are one active site. In active site, maybe one metal ion or maybe multi-metal ion also active sites are there. Usually metal ions are there. So, let us talk about metalloenzyme, that means always metals are there. So, in this metalloenzyme, this is my active site. Okay. And this protein is essential in biology. So, this proteins do all the biochemical reactions. Okay. They are catalyst in effective chemical reactions in our body. So, they are essential. Without a protein, we will die. So, proteins are workhorses. How they work? How they work? They work, suppose this metal ion is the active site, means where action takes place. Here is the site where action will take place. If some action takes place, suppose here, suppose this is tryptophan, this one is tryptophan. Okay. How do I know this is tryptophan? Because I know X-ray structure of this. Okay. Or from NMR, say 2D NMR, you can somehow you know that tryptophan is here, and when this particular metal ion will do chemical function, when it is doing function, this tryptophan was like this, just an argument. This tryptophan was like this, and when it is not working, when this metal active site is not working, this is in a relaxed position. Okay. So, tryptophan, just assume tryptophan is here when it is energized or it is about to react, this active site will react, then tryptophan will be like this. Okay. And when this active site is not reacting, tryptophan will be stable, highly stable. So, they always do like this. Okay. So, what I do here? I put a metal ion, I put another synthesized fluorophore here. Maybe I will put a different color, for red color. This is my synthesized fluorophore. Okay. And what will be the, for tryptophan, it will be synthesized fluorophore. Now, let me tell you another story. So, this is fluorophore 1, this is fluorophore 2. Fluorophore 2 is natural and fluorophore 1 is I put it here chemically. Okay. So, let me tell you another story now here. This is important. So, this is intensity. Intensity arbitrary unit, okay, and this is wavelength lambda, wavelength in nanometer, say. Okay. Now, this is okay. Now, this is excitation of this. You can excite it in a particular excitation spectra, okay, and then it will emit. If you excite it, it will emit. Emit is always at longer wavelengths. That we know from our knowledge of fluorescence. Fluorescence, you have excitation spectra or say near like absorption spectra. So, absorption spectra, forget if you are not familiar with excitation, let us call it absorption spectra, then this is emission spectra. Emission spectra is always like a mirror image of absorption spectra, except they come at longer wavelengths here. So, this is one. Now, for my fluorophore 2, this is fluorophore 2 say, this is fluorophore 2. So, now I do with the one I put fluorophore 1, fluorophore 1. Fluorophore 1 is my compound. So, there what happens? This is absorption spectra and this is emission spectra. Okay. It is just a drawing, it cannot be like this perfect. So, this is important. This is emission, 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 and this is absorption. If you want, I can put black. Black is suppose natural and this red is my compound, emission, absorption. So, what does this mean? This means, this picture means emission spectra of one fluorophore means natural fluorophore. Emission spectra of natural fluorophore and absorption spectra of my fluorophore, they have some overlap. They have some overlap. This is the overlap area. In that case, what happens? Energy will be transferred from this excited, this emission. So, energy will be transferred from here to here. Okay. So, I will tell you again, there are two fluorophores, fluorophore 1, fluorophore 2. If the emission spectra of fluorophore 1 overlaps with the absorption spectra of fluorophore 2, then there will be energy transfer from fluorophore 1 to fluorophore 2. Okay. That means, fluorophore 2 is excited. So, therefore, what will happen? If I excite this fluorophore, this will be excited and it will emit. This is known as Fred Forster did that lot of work. Forster Forster resonance energy transfer. Okay. Forster resonance energy transfer. So, because so this is called resonance energy transfer. So, what I do it again? There is fluorophore 1 and fluorophore 2. I should write here, this I made a absolute mistake. This will be fluorophore 1. So, from one fluorophore 1, it will absorb light, okay, absorbs light energy, go to excited state and it will emit. Its emission spectra matches or overlaps with the absorption spectra of another fluorophore. When that happens, how do I know it matches? Because there is overlap. So, this is the matching point. When it does like that, then energy will be transferred from here to here, because this will be in resonance. So, that is called Forster resonance energy transfer. In short, fret. So, this fret works in solution phase. Okay. This fret works in solution phase. In solid phase is not, it does not work. It will work in this will work in solution phase. Most importantly, efficiency of fret, how much efficient? Efficiency of fret will depend upon distance between the two fluorophore. Efficiency of fret from one to the other will depend upon how far they are, 10 angstrom, 12 angstrom or 5 angstrom, things like that. Okay, they can be 10, 12 angstrom, no problem. That is point number 1. Point number 2 is that my recipient, this fluorophore and this fluorophore, these two fluorophore must be oriented properly. Okay. If this fluorophore is like this and my this fluorophore that we synthesize fluorophore and my cryptan, that tryptophan we have zeroed in, this tryptophan, I said tryptophan, yes, I said tryptophan. If this tryptophan, it also should be matching orientation. Suppose it is orientation is this. If the orientation is this, then it will not match, then the fret will be not be possible, fret will be minimum. Okay. But if it is matching and if the distance around 10 to 20 angstrom anywhere, then fret will be very successful and all energy will be transferred. Okay. So, this is fret. Now, let me show some example and do accordingly. Then I will come back here. See, let me do this. First write this compound, this is very important. You have to understand the photophysical process. Occasionally I make goof. This. Nice. Okay. 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 So, now this particular compound cryptan, okay, is very easy because you can sequentially add. I have sequentially added anthracene and I have added another compound, another fluorophore. Anthracene is a fluorophore and this diazo, remember, okay. So, this compound, this is nitro here. Okay. Now, it goes to about 10 to 30 angstrom, this work. Now, what happens is anthracene, if you look at anthracene emission, okay, if you look at anthracene emission, this is anthracene emission. So, anthracene absorption is somewhere here and this is say around 450 nanometer. This is intensity, this is lambda nanometer wavelength. Okay. Now, what is the emission and absorption of this diazo? Diazo absorbs here. Diazo is simple, only one peak, not a peak like this, but simply a peak. This is my diazo. So, what do I see? I see that there is a lot of overlap. There is a lot of overlap. Because of this overlap, what will happen? And dye absorption. This is emission, this is absorption, okay, of diazo, and absorption of dye of this one will come somewhere here, okay, and emission is here, emission of diazo, because emission is always comes at longer wavelength. So, therefore, what will happen? If I put a metal ion here, I am exciting it, say copper 2, you know that with a copper 2 gives a very strong emission band. I showed you, it gives a very emission band. So, emission band of anthracene, because nitrogen lone pair is there. But what I see, if I excited this anthracene, I do not see any emission of anthracene. I see this, very little. This is anthracene emission, and I see completely emission of this one. This is the emission of diazo fluorophore. Okay. So, the time is not there right now. So, I will stop and start this work again tomorrow, again in my next class. I like to complete it. I like to tell you in detail that what does this mean and how it is very important in understanding. FRET is a very important fluorescence technique to understand physiology. Thank you very much.